Let's turn the mic on. Can everybody hear me? That's good. That's not working. Okay. Hello, everyone. I am thrilled to be here. It is my first PyData conference, and immediately getting the opportunity to talk about one of my main interests, which is machine learning, is really exciting. As Jonathan already mentioned, my name is Florian. I'm the project lead of the ad targeting team at Yelp. And in the next 30 minutes, I'm going to share the most important pitfalls and lessons we've learned at Yelp when working on the CTR prediction system. And my hope is that by doing so, this will allow you to run your own machine learning applications with fewer surprises, improved understanding of model behavior, and overall better results. And while I'm going to use CTR prediction as the running example throughout the presentation, I will, well, the lessons that I'm going to talk about, I think they generally apply to machine learning applications, well, in general. Before we jump right into the details, though, I want to briefly introduce Yelp and also CTR prediction. First of all, just by a quick show of hands, who in here knows about Yelp? Yes, almost everybody. That's what I was hoping for. Positive feedback is always great. So I'll keep it really brief. Yelp's mission is to connect people with great local businesses. That is really what we're all about. And as you can see from these numbers, so we have a lot of users, we have a lot of data. So the first icon tells you that we have more than 90 million monthly unique users just on mobile. We have more than 100 million reviews in our platform that we can work with. And probably most surprising to you, we have, or Yelp is present across 32 countries around the world. So Yelp has a really global footprint at this time. And that's already everything I wanted to say about Yelp specifically. Let's talk about CTR prediction. So first of all, CTR, it stands for click-through rate. And since I'm going to use pCTR throughout this presentation quite a lot of times, that simply is predicted click-through rate. And the question we're trying to answer with CTR prediction is when we want to show an ad, what is the probability that a user would click on that ad? So if you look at the example over here, is it 9%? Is it 5%? Is it 1%? And the reason we want to know that is because if you think about it, whether a user clicks on, like, this probability is really a good proxy for relevance. And we definitely want to show relevant ads because that's good for all involved parties. That's good for the users, obviously. It's good for the advertisers and also for Yelp. And as you've seen, we have a lot of data, a lot of users, so Yelp is pretty big. And more than 80% of the revenue that Yelp makes comes from local advertising. And CTR prediction is really at the heart of that local advertising system. So in essence, CTR prediction is really important for Yelp. How do we do it? We use logistic regression with thousands of features and millions of training data and also testing data. And now you might wonder, why is there a dog on this slide? And the answer to that is we name all of our models after dog breeds. The current model is called Kuvas, a Hungarian dog. And just for the fun of it, let's have a look at previous models. So we had French Brittany, Icelandic sheepdog, and also the Korean Jindo already. So that's a great side effect of working in the ad targeting team. You get to know more about dog breeds than you ever thought you would. Okay, let's jump into lessons learned. So as you've seen, the model we're using is really, I would say, a large-scale model. Thousands of features and millions of samples. Let's dial it down a little bit, though, and think about how would an architecture look like if we were just to start out with CTR prediction. And the one that I was able to come up with is this one. So as you see, it's split up between the offline and the online world. And I'm going to start out in the offline world with the data, which is where it usually begins for a machine learning or machine learning engineer or data scientist. And I'm just going to assume that we have the data already. So once we have data, we can train a model on it. And once we have that model, we can put it in some online production environment, maybe into a service, where it can make predictions. And in the case of CTR prediction, we were very fortunate that we get automatically labels, user feedback for every advertisement that we show, because the user either clicks on it or he doesn't click on it. And now when we, if we log the input data to the model and also the user feedback, then automatically what we get is basically all the data that we need to train a new model. And that really completes, so writing to the logs completes the whole cycle, and we can train new models, again, with newer data, and do that over and over again. And this is the basic architecture that we're going to work with throughout the presentation, and I'm going to step-by-step point out some areas of where we can improve the architecture and talk more about that. And those lessons that I'm going to talk about can roughly be grouped into infrastructure and also model comprehension. So let's start out with infrastructure. Oh, by the way, because it's dogs again, the corgi, well, the mascot of the ads team is the corgi, so you're going to see a lot of corgi slides. Okay, so this is our current architecture. Now, I was mentioning logs before, and the first thing that I want to point out is that you should log at the source of the online prediction. And what I mean by that is the place in your system where you make the prediction, you should also log it. If it's in a service, you should log that, the input data in that service and not somewhere downstream. The reason for that is that if it happens downstream, then a developer that works on that part might not know that it's important for floating point numbers to have a big amount of digits of precision and not just round it up to 2 or 1 digit of precision. And there are all kinds of things that can happen. And once you change the actual data that you're logging from the one that you see online, you have corrupted successfully your offline training data, because your training data is different from what you see in the online world, and that is exactly what you don't want to happen. So it might seem like a minor detail, but logging at the source of the online prediction, that can save you a lot of hassle. So we got that into our architecture. Now, still, how do you know, even if you log at the source of the online prediction, how do you know that you're logging the right thing? And that's where prediction verification is what we call it, comes in. What you do there is you look at the logs that you've written, and you make a prediction with the same model again offline, and you see whether a prediction you make offline gives you the same result as the one that you make online. If it does, then you know, okay, it seems to be matching, it seems to be good, there is not a problem. But if it doesn't match, then you probably should call in your engineers to look at it more deeply. We got that into our architecture. Now the final point for the infrastructure lessons that I want to make is this one. It's to make the offline iterations as fast and scalable as possible. I think we all know that machine learning is not a discipline where you have hard rules to come from A to B. It's very much explorative. You're trying out some methods, approaches, and in the end you evaluate it, and then you see, okay, it's working or it's not working. And in other words, you have a lot of iterations that you're going through. And the faster and more scalable these iterations are, the more you can iterate and progress. So this is really key, I think, to having fast results. And one part that I want to point out there is automation. So if a developer has to kick off every job that is involved in the offline infrastructure, like evaluation, model training, everything, then that takes quite a while. Why not just automate everything? So you kick it off once, the whole pipeline runs, and you get an email of the evaluation in the end in your inbox. That's much more, well, it's faster. And also automated visualizations. I personally think visualizations are great, but if they're just hanging out in some IPython notebook that some developer coded up I don't know, a couple months ago, and only a couple developers know about it, and sometimes they use it, but not always. It's not too helpful. If it's a useful visualization, it should really be included into your evaluation report automatically. So you see it every single time you do it, and then, I mean, it can't hurt to look at some helpful visualization. So it's always on your mind, basically. And yeah, do we at Yelp also, well, what does the infrastructure at Yelp look like? So this is an overview of the offline training infrastructure at Yelp. And we start out with merging the logs. Like I mentioned before, we have, on the one hand, the input for the model prediction, and on the other hand, the user feedback. So we merge that together. Then we sample down, because we're in a fortunate situation where we actually have too much data. That we don't want to process all of it. And then the whole pipeline begins. First, there is feature engineering, of course. You want to think about new features, implement them, add them to the model. And then you kick off the pipeline. It's feature extraction, model training, and evaluation. And in the end, you get an email that tells you either, yeah, you got to start over again because it's not good enough, or it's good to go. You can push it to production. And as you might have noticed already from the background image, everything in here that you see, except for the feature engineering part, is really in the cloud. We use MR job in combination with AWS EMR to run every job, which makes it every job in the cloud, which makes it very scalable. And especially the model training is, well, that's always at the heart of a machine learning pipeline, I would say. And there we use Spark with a great success so far. So the training of models is really on the order of minutes for us. Keep in mind that we have to do cross-validation and grid search, so it takes a little longer, but on average, one model is on the order of minutes. Yeah, that's as much as I wanted to say about that. So these are the lessons we've learned so far. Log at the source of the online prediction, verify your predictions, and make offline iterations fast and scalable. Now let's talk a little bit about model comprehension. And hopefully we'll see more than this poor corgi. Again, this is our current architecture. And there is one piece that is utterly missing right now. And I hope that many of you have noticed already what I mean. And it is evaluation. Evaluation is super important when it comes to machine learning. And I'm not going to talk about the standard stuff that you're going to do, the cross-validation, having a holdout validation set, or doing A/B testing online. What I want to talk about instead is that you should focus on a single metric. And to motivate that a little bit, think about a system where you have two very important metrics, and you're always looking at those two metrics to figure out is it an improvement or not. And then you make a change in your model and it improves one of the metrics, but the other one goes down. So what are you going to do? Probably you're going to have a long discussion with your fellow engineers and maybe make a decision at the end, but then, as it so happens, the next time the one metric goes down, the other one goes up. So you're just not going to make a lot of progress. What instead you should do, I think, is to figure out one metric that works for you, one that is really your objective. Take your time to do that, and then focus only on that single metric for making decisions. You shouldn't trust it blindly, though. You should always have other metrics in the background that you do a safety check on. But yeah, focusing on multiple metrics, I think, is a recipe for disaster. Our metric that we're using is mean cross entropy, which is the mean of the negative log likelihood of the logistic regression model. And that is really what we use for making decisions on a day-to-day basis. Now, again, we have alternative metrics as well, like calibration plots and other things that we look at. But this is really, the big one. Now, I've talked about visualizations a little bit before already, that I'm a big fan of visualizations. And I got to say, again and again, I'm amazed by how much information you can convey with a good visualization. It happened a couple times already that we just finished, creating or generating this visualization, and then we noticed immediately, oh, there is room for improvement. Like, we could split this feature out into two, or we could do a piecewise linear instead of just having a linear relationship. It makes it super obvious if there's something wrong with your model. And one of the tools, so we started to use and generate more and more visualizations just to understand what's going on. And one of the tools that we're using a lot for that is Zeppelin, which allows us to do very exploratory work over a big amount of data. And to give you a few examples of the visualizations, the first one that you see is the feature contributions. In other words, which feature is really the most important for your model? Which one drives it the most? And you can see that the features are ranked on the y-axis, and each bar, indicates one feature. And if it's to the right, then it's good for the target variable, in our case CTR. If it's to the left, then it drives it down. And not only does that give you a great overview of what's happening inside your model, it also tells you that maybe there is this really, really important feature that you have that has also a lot of uncertainty in it. So maybe you want to focus on dialing down that uncertainty a little bit and basically get your priorities straight. Add a prior to it, or do whatever tool you have at your disposal. And the second visualization here is also very useful. It's I would say the classic feature plotted against the target value, the target variable, CTR in our case again. And here, for example, you can see the count is on a log scale. So you can see that the very first bar, it might make sense to split that out into another feature because it doesn't really correspond with the overall trend that we see with the linear one. That's just one example. Okay, so that was evaluation, and it sits at the center of the whole architecture. It's both offline and online because there's A/B testing as well, which I mentioned, so you definitely want to do that. Now, the next topic that I want to talk about is personally to me the most interesting, and it is thresholds. Now, by thresholds, I don't mean just a normal threshold on a feature or something. What I mean by thresholds is putting a threshold on the prediction of your model. In our case, that means sometimes the predicted CTR is really low, which tells us that the relevance of this ad wouldn't be very high. And in that case, we'd rather not show the ad at all, because that's hopefully good for the users. There's no opportunity cost to show ads. The effect that this has, though, is that automatically the online world that we're seeing is different from our offline training data. Just because of the threshold, because we don't get those advertisements that are below the threshold. We don't get user feedback on that, so we don't have it in the training data. So let's see how that plays out. What you see here is, for three models, you see the CTR on one hand, which is let's say we know the true CTR of an advertisement, and then the p-CTR, what the model thinks it's going to be. So the first model, let's assume it's doing a really good job around the threshold. Oh yeah, the line is really the threshold here. So either it's above or below the threshold. So the first model, let's assume it's doing a really good job around the threshold, and sometimes it makes a little mistake, but it's very rare. So we don't see a lot of these impressions in our training data. That, on the other hand, means that the second model that's based on this training data doesn't know how to behave around the threshold and makes a lot of errors, which is bad on one side, but on the other side it's good because we're getting those impressions into our training data again, which lets our next model be good around the threshold again. So it's really this up and down, this periodic up and down that we really do not want to happen, right? We don't want to have that. So what can we do about it? So one idea is, usually when you do offline training, you always have some time frame over which you select your training data. And now if you do more frequent retraining, then what you might want to end up with is that you have the predictions from multiple models that have been online in your training data. Now, the first model was good, the second model was bad, the third model was good. Overall, on average, we get a good amount of bad advertisements into our training data, which then, if we train over all of that, lets our next model do a decent job around the threshold. So it basically smoothes out that trend. It's only a fix, though. It doesn't really solve the problem because there's still a little bit of up and down. But it might help you to not get interrupted by this behavior with all the other stuff that you're trying to measure and trying to improve. Now, a better way of tackling this is to do a deliberate sampling of bad ads. That from time to time you see, okay, this model would put this advertisement below the threshold, but let's actually slip it through so that we get a little bit more of exploration in that area, and we can then use that or profit from that by having it in our training data and being better at exploitation with the next model. And ideally, you want to do that in a smart way so that you show as few bad ads as possible. Obviously, that's the harder one. Yeah, but that's, I think, the goal that you should strive for. Now, there is one more point that I glossed over before when talking about this behavior, and that is online. When we have A/B testing, for example, we have a couple of models online that we compare against. There, only what we see is really this part of the data. So in other words, if you look at model 1, we do not see the strength of model 1 that it has of ads that are below the threshold, that it keeps below the threshold, because that's hidden to us. And we also do not see the same thing, the strength or the weakness of models to keep advertisements that would be above the threshold, also above the threshold for the predictions. If it pushes it below the threshold, we're not going to see that. So our evaluation will always be a little bit biased. Now, if you think about this scenario where we have just normal A/B testing with the current model in green, which maybe gets 90% of the data, of the traffic, and the new model, which we hope is going to do better, gets, let's say, 10%. Then what we came up with to solve this overall problem of not having that data available around the thresholds is to do rescoring offline. So all the impressions that the current model would have seen, all the ads that the current model scored, we would score it offline with the new model as well. And that would tell us then, is the model better for the ones that, let's say the current model puts something above the threshold, it should be below the threshold, the new model knows that, it puts it below the threshold. We would get that into our evaluation. And vice versa for the ads that the new model has seen online. And then we take all of that and do the evaluation of the whole thing. That's what we call combined rescoring. And so if the traffic is 50-50, then that's an absolute fair comparison between two models. All right, that was model comprehension. So to recap, evaluate, 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 and be aware of those threshold effects. Now, there is one more aspect that I'd like to talk about that I'm going to add to this whole architecture. And because it's so important to me, or I think in general, that is, it's got to be right at the center, and it's simplicity. So I believe that simplicity should be the main guideline, or one of the main guidelines for software engineers, and especially in the machine learning area, where the concepts that we're dealing with are complex by nature already. And what do I mean by simplicity? So I think that it's not a bad idea or even a good idea to start out with a rule-based approach if you don't have anything else. What's wrong about it? You get a better understanding of your problem domain, and in the same vein, it's with simple models. Start with simple models. I know there's a big hype about deep learning, but if you start out with using deep learning for the wrong kind of problem, you might not be so successful. And Occam's razor goes in the same direction. If you have two models that perform about the same way, choose the simpler one. I totally agree with that. Now, the next point is appropriate metric. I talked about that. Try to pick one metric that really resonates with your overall objective, and that will simplify your life. And then there's this topic of documentation. I'm pretty sure that, yeah, probably nobody in here likes to do documentation. But on the other hand, it's super important. It is, if you have some machine learning related code and you add documentation to it, automatically it makes it so much simpler, just by adding 1 or 2 lines of, text. And there's this tech talk, Simple Made Easy, by Rich Hickey, who is the creator of Clojure, which I think is probably the best tech talk that I've ever seen. So if you haven't watched it, I can highly recommend that. All right, so adding simplicity and well documented, and that completes our whole architecture. And again, to recap the lessons, above all, keep it simple. And that's all from my side. Thank you.
So we're going to open it up for any questions that anybody has for Florian. And if we can just repeat the question.
Okay. Yeah.
So I'm curious, for ads that the offline model determines of across the threshold, would it help if you had some small probability of exposing them to users anyway, just for the purpose of improving your online scoring model?
So let me see. So you're basically going for the better version here, to do deliberately sample, or what is the question exactly?
Instead of having a strict threshold of saying below this, we simply don't show it at all.
Yeah.
You say below this, we have a smaller probability of showing.
Yeah. So the question is, instead of having a strict threshold below which we don't show any ads, have a small probability that we're, even though an ad is below that threshold, we show it. And that's exactly what I was trying to convey here with the better method, where even if the model thinks that it's below the threshold, you might want to sample it and let it through, and then in the end show it to get some feedback. So you explore more. And yeah, ideally the probability of that happening would be bigger around the threshold, like close to the threshold, and really small if it's, close to probability of, close to PCTR of 0. Does that answer the question?
Yeah, sorry,
Great.
I didn't get that.
Any more questions? Yes, please.
What is the threshold?
What is a threshold? It's a strict rule where, let's say, if the predicted click-through rate is above 1%, we're going to show it. If it's below 1%, we're not going to show it. So it's a strict rule that you add to the whole process.
So it's 1%?
You can choose the number that you want. I mean, it's 5%, 10%, whatever. Whatever fits your problem. Yeah, there's one more question. Combined rescoring. So the question is to explain combined rescoring again. I can absolutely understand that it's not super clear because it's quite an involved topic. So the point is, if we look at this, and let's say those 3 models, all of these are online, and we make predictions online with these 3 models. And what we don't see, like all the data that we have available for our evaluation algorithms is only the green dots. So if one model is really good at keeping all the ads that should be below the threshold, also keeping them below the threshold, we don't see that at all in our data. And now with combined rescoring, if let's say the current model is not as good at doing that, but the new model is really good at keeping them below, then the current model will have some ads that it makes the wrong prediction that go above the threshold. But the new model will then say, if we do the rescoring of that, it will say, oh, okay, it should have been below the threshold. And we do get user feedback on those ads. So we can really tell whether the new model was better in that sense or not. All right. Any more questions? Okay.
All right, let's give Florian another hand of